Important features of the equilibrium constant. In this video, we will learn about some of the important, characteristic features of an equilibrium constant. The first thing is this equilibrium constant, we apply for a particular reversible reaction only when the system has attained an equilibrium, right? So that means if you have a reversible reaction, suppose we have A plus B and they react and form, the C and D, these are the reactants, and the C and D again, reacts and form the A and the B. This equilibrium constant, which we normally write it like this, which is actually the concentration of the products C and D and divided by the concentration of the reactant C and the B. This is how we write down the equilibrium constant. This particular equilibrium constant actually, it's the ratio of the concentration of the products by the reactants, right? And this, equilibrium constant, we apply it only when you have attained a state of an equilibrium, correct? That means when the rate of forward reaction is equal to the rate of backward reaction. That's what, we call as a state of an equilibrium, correct? So that means this equilibrium constant is applicable. We apply it only when you calculate it only when you have attained a state of an equilibrium. The value of this equilibrium constant is independent of the initial concentration. So whatever you take the reactions here, the concentration of the reactants here A, B, correct? The ratio is going to be same for a particular reaction, correct? That means this equilibrium constant K, it doesn't depend on, what we take the initial concentration, correct? If the initial concentration is, in any proportion you take it, so whatever you take the reactant concentration, the equilibrium constant, which is actually the ratio of the concentration of the products and the reactants, the molar concentration ratios, that will remain same, correct, for a particular reaction. Equilibrium constant is temperature dependent. That means, if you have a particular reaction, let me write down the reaction here. Suppose we have a hydrogen and the iodine. This is under equilibrium with HI. So for this particular reaction, the equilibrium constant, which we can write it like HI, concentration of HI power 2 by concentration of hydrogen and iodine. This, constant, equilibrium constant here will remain constant. It will have a particular fixed value as long as you keep the temperature constant. We have this reaction mixture at a certain temperature, let's say at 25 degrees Celsius. At 25 degrees Celsius, it has some value, correct? So for example, let's suppose, at 25 degrees Celsius, suppose here the equilibrium constant for this particular reaction is 50, right? Just for an understanding. If this constant for this particular reaction is 50, then the same value will change for the same reaction if you change its temperature. Suppose you change the temperature from 25 to 50. At 50 degrees Celsius, for the same reaction, this equilibrium constant will be different. That's what we mean by temperature dependent. That means this will change if you change the temperature for the same reaction. And this equilibrium constant for a reversible, reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. That means, if this is our reaction here, correct? If this is our reaction and you find the equilibrium constant, which is HI square by H2 and I2, and if I reverse this reaction now, if I write down the same reaction like this, HI, 2 times HI, it's now under equilibrium. Now with the hydrogen and the iodine, if I write it like this way, so therefore the equilibrium constant for this particular reaction, that will be written as concentration of hydrogen and the iodine divided by HI power 2, right? So what will be that value, if you have the same reaction at the same temperature, even at the 25 degrees Celsius, correct? You keep the temperature constant, only, inverse the reaction. Now, the value for this equilibrium constant will be here 1 over 50, because for this reaction it is 50, now it will be 1 by 50. So if you reverse a reaction, the new equilibrium constant will be 1 over the previous, equilibrium constant. Correct? If you have the same temperature. So keeping the temperature constant, you reverse the reaction, so you can find the equilibrium constant that will be 1 over the previous equilibrium, value. And, this equilibrium constant, it gives us the idea about the extent of the reaction. So the value of this equilibrium constant, it gives us an idea how far the reaction is towards the reactant side and the product side. If you look at the previous equation here, when I write down this H2I2 and gives HI, and the equilibrium constant is 1/50. So this value here, the higher value of this K, actually it tells us that there is a lot of concentration of HI and very less concentration of H2 and the I2. So that means here this 50, the value of the 50, it tells us that the equilibrium is more towards the HI, less towards the reactant side. That means in a reaction mixture you have more HI concentration than the the hydrogen and the iodine. And look at here, what we got here, this value 1/50, very, very low value. So it will be around 0.02 value here. So very lower value of this equilibrium constant means that this one is less, isn't it? Hydrogen and the iodine, it is less. So that means for a particular reaction, this extent of this reaction, how far the equilibrium is to the reactant side and the product side, is it more having the concentration of products or the reactants, you get it from the value of that equilibrium constant. Suppose if I write down here a reversible reaction A plus B, which actually is under equilibrium with the C and D, and if here if you suppose we have a equilibrium constant which is equal to 1, so what does it mean? If the value here is 1.0, that means the concentration of C and D and A and B is same. That's why the ratio is same, correct? So this 1, it means that you have 50% products and 50% reactants. Now if it is more than 1, so more than 1, it means that you have higher concentration of products and lesser concentration of reactants. But if it is lesser than 1.0, that means here we have the more reactants and less products. And this equilibrium constant, for a particular reaction, it will be same whether you carry out a reaction in presence of a catalyst or in absence of a catalyst. So whether you add a catalyst or not, it doesn't, it will not change the equilibrium constant, correct? So whatever is the the ratio here for this particular reaction, we can write it like the C and D, concentration of C and D by concentration of A and the B. If you carry out this reaction in presence of a catalyst or in absence of catalyst, its value will be constant as long as you keep the temperature constant, correct? So that means catalyst again does not alter this equilibrium constant, right? It does not change the equilibrium constant for a particular reaction. Catalyst has no effect on the value of this equilibrium constant. Rather, the catalyst will only help, right? A catalyst will only help in the attainment of that equilibrium, correct? So you can get a reversible system under equilibrium conditions very quickly when you use a catalyst. In absence of a catalyst, it may take some time, but the catalyst does not change the value of this equilibrium constant, right? It will be same. That means this equilibrium constant, it only changes when you are changing the temperature for a particular reaction. So you have a particular reversible system. There's only one factor that will actually change the equilibrium constant value, that is temperature. Hope you got it. Thanks for watching the video. Bye for now.